Okay, so this is lecture 9. So in this class, we will be talking about the constraint forces. So we will be taking example of two masses M1 and M2 which are connected by this massless rod. So there is a massless rod which connects M1 and M2 masses, and external force F of T is being applied to this system directly to M2 and then indirectly to the M1 also and to the whole system. So am I audible?
Yes, sir. Audible.
Okay. If you have any doubt in between, you can stop me and ask the question. Okay. So M1 is the mass of this object and M2 is the mass of this object and L is the separation between the two masses. Basically, we are treating these two masses as point masses. M1 is point mass and M2 is point mass. So we, as usual, want to get the equations of motion for this system. That is, we want if what is the position of this M1 as function of time and position of this M2 as function of time. So we want this x1 and x2 at any instant of time. And this f of t, which is external force applied to this system, this is basically known. For example, this f of t may be equal to t square or sine of t, or maybe some constant force, 2 Newton, etc. Okay, so the problem is that if we are given m1, m2, f, and we are given L, can we find the equations of motion? So this is the question. So let's try to solve this and first what we will do, we will draw a free body diagram. So we have mass m1 and since it is being connected with m2 through this rod, so we cut this rod and we see that there is a tension in this rod which is T, therefore T tension acts on this M1 in this direction. Similarly, there will be T acting on this M2 and there is obviously this F of T. I am writing this as F of T in general. This may be constant and other stuff. Okay. So, uh, we don't know this tension. And the thing is that you might be thinking that we will directly apply Newton's second law like we have for M1 and M2. That is, the net external force on M1 is nothing but M1 times A1. So, and similarly for this. But the thing is that we don't know this tension, what this force is equal to. And like in previous cases, we have spring, we have, for example, gravitational two-body problem in which there was gravitational force. We don't have any such constitutive law for calculating this tension. By that I mean all the forces which are present here, we can't write them as a function of distance, velocity, and time. If you remember, let me quickly go to whiteboard. Okay, is whiteboard visible to you? Yeah, is whiteboard visible? Hello, hello.
Yes, sir. Yes.
Is whiteboard visible?
Yes, sir. Whiteboard is visible.
Okay, so I am saying that in previous cases, like if we take this M1 and we were taking M2, so there was a force F due to this F on 2 due to first, and we saw that we could write this F12 as gravitational constant time as m1, m2, uh, r12 upon r12 cube. So we saw, so you can see that this force of attraction we could write in terms of this position vector. So this force was function of r. Sometimes also, for example, if there was a drag, we also saw one example where we used that drag. Let me make this smaller. Okay, so we also saw one more problem in which we had some spherical ball and it was moving with velocity v. We saw that there was a drag force Fd, which was a function of this velocity. If you remember, we so this Fd basically was function of velocity. So in general, if you solve these forces, these will be some function of r, which is like here, or maybe function of velocity and function of time. So basically, you will mostly find that the forces which you have in your system can be defined like these things. But here we have this tension force in the massless rod, and this cannot be represented like this. So this we call this tension as the constant force. Okay, so how we can deal with such problem? I know that you might have done this problem in maybe 11th or 12th class, but let us rewind this thing so that we get more intuition about this problem. What was the fault? Or maybe you at that time have not given thought to this thing, that what is the problem lying with this system. So the first thing is that we can do linear momentum balance for M1. We can do linear momentum balance for M2. That is applying the Newton's second law or linear momentum balance equation on each of the masses. So and then adding first and second, we can get this F equal to M1 plus A1 plus M2 A2. This is simple. You add these. So these T get cancelled. Okay. And from the geometry of the figure, if you can see, so basically what we have, uh, okay. So what we have is, oh, what is something wrong with it? Yeah, now it should work. Okay. So basically we have M1 and we have M2 and there is a force which is being acted upon these two masses m1 and m2, and the separation between these two is L. And this is the position x1, and this is the instantaneous position of m2, which is x2. So we can see uh, that x2 minus x1 is always equal to L. This is the fixed length, and this is not something which can stretch. This is the assumption we have made. Okay, you can differentiate on both sides. We will get x2 dot minus x1 dot equal to 0, and then again differentiating, that gives us x2 double dot minus x1 double dot equal to 0. X2 double dot is nothing but acceleration of mass 2 minus acceleration of my 1 is equal to 0, which is nothing but a2 equal to a1. So basically this says, so this was a constant, x2 minus x1 was a constant. So this basically says that acceleration of a2 and a1, these are same. Okay. So when we enforce this condition here in equation 3, we can get F equal to m1 plus m2. Okay, a will be common. So this acceleration is nothing but F divided by m1 plus m2. So this acceleration A, it is the acceleration of whole system. That is, every point of this system is moving with the same acceleration. And this is the acceleration of m1, and this is the acceleration of m2 also, and obviously the acceleration of the center of mass. Okay. Uh, and this is our equation of motion, because we were looking at the acceleration. If we know the acceleration of the mass, we can integrate it over time to get the velocity, and then again we can integrate it to get the position. So, any question till now? Hello? Any question? Hello?
Clear, sir.
Okay. Okay.
Yeah. Actually, sir, this is mic problem, sir. Sort of.
Okay, Mike. Okay. Uh, let us look another method for solving the same problem. So, uh, so basically the problem here is that we don't know one force, which is tension, and which is there in the system. So if you don't know something and you don't care about it, so just ignore it or just kill it. This is something you may call as a rule of thumb or whatsoever. So we don't know tension, so we don't want this to come in our equations. Okay. So we have read in the previous lectures that if we have a system, and here the system is M1 and M2 jointly, we can treat this as a system. And we know that for a system, we can write summation of all external forces is equal to M total of the system into the acceleration of the center of mass. This we have read in the previous lecture. Okay. So what is the net external force? There is only one external force, which is F of t. And I am writing this F of t as F, just F. So we have F, which is equal to M total is nothing but M1 plus M2. There are only two masses in this system. And acceleration of this center of mass, we can write it like this. Okay, let me go again to whiteboard. Uh, Okay, so basically we know that xg, that is the position of center of gravity, is nothing but m1 x1 plus m2 x2. If we have only two masses, and then this is m1 plus m2. Now differentiating this equation, we can get this equal to m1 x1 dot plus m2 x2 dot upon m1 plus m2. And again differentiating it, we can get xc double dot equal to m1 x1 double dot plus m2 x2 double dot upon m1 plus m2. Xc double dot is nothing but acceleration of center of gravity. M1 x1 double dot is a1 plus m2. X2 double dot is a2 upon m1 plus m2. Okay, so this is what I have done here. So m1 a1 plus m2 a2 upon m total. M total is nothing but m1 plus m2. So ag I have replaced it by this thing, and then we can see that m1 plus m2, a is common, so we can a1 and a2 are equal due to the constraint equation, so we can cancel out these things, and we get f equal to m1 plus m2 times a, where a is nothing but equal to a1 a2 and acceleration of acceleration of center of. So we got the same equation which was there. So okay, so it is fine. So now what we will be looking at, since this is a very simple system, but we
Sir,
will apply, yeah,
sir, in second method, a1 is equal to a2.
yeah.
How a1 is equal to a2, sir, in second method?
Okay, how it is equal? Okay, let us go. So actually the constant equation is same, which I have wrote, where I wrote that. So this, okay.
Constant equation
Alright.
first method and constant equation second
Yeah,
method is same.
these are same. These are
Okay,
same.
and then it is clear, sir.
This is
I
the same system, and the equations are constant equations are same.
okay, okay. Sir. Then
Okay.
continue.
Okay. So now we will be looking another by another method, which is very powerful method, but you will not get the essence of this method from this example, because this example is very simple and you have various other ways to solve the problem. So you can easily solve this problem, and because you have so many times solved this problem, and you will not appreciate this method. But to understand how the method works, I think this is the proper example to get started with. Okay, so what we will do, we will write the FBD for first and second. So from FBD of first, we can write A1 times A1 equal to tension. Similarly, for free body diagram of second object, we can write M mass M2 A2 is equal to net external force, and for that the net external force is F minus T. Is it okay? Are you following me?
Yes, sir. Yes, sir. Yes, sir.
Okay. So the constant equation we have seen is A1 minus A2 equal to 0. So in previous methods, what we were doing, we were either eliminating T or solving for T or substituting. So we were doing like such things. But here what we are doing, we are taking each of the system, we are taking each of the mass, we are writing the linear momentum balance equation for each of the mass, because we know from the Newton's second law, we can write it for uh, every mass and every particle. And we don't care if there are some unknowns, let they be there, and we write everything which we know. So there is constant equation, we write it as it is. But yeah, so our constant equation was in terms of position. We differentiated it, we got the constraint on the system in terms of velocity. We again differentiated the equation to get the um, constraint in terms of acceleration. So this is basically the constraint. What is the constraint? That the distance between the two masses is fixed and that is equal to L. Okay, so this is the constraint, and that can be reflected by this thing, a1 minus a2 equal to 0. That is the acceleration of 1 minus acceleration of 2, this is equal to 0. Or you can equivalently say a2 minus a1 equal to 0. So there is no difference in writing it as such. So now what we will do, so we have so let us shift to whiteboard. I think it is better to do stuff here. Okay. Okay. So what I am saying that we have M1 and we have M2 here. So there was a force F and there was a constant of L, and we just write the FBD for each. So there is M1 which is having tension in this direction, and there is M2, the tension acts in this direction, and there is force external which is, so write this FBD for this, we can write it as M1 times acceleration of first equal to T, and we can write, yeah,
Yes, sir. M2A2 is equal to F minus T. Okay, sir.
F minus T. So this is the second equation, and the third one is that A2 minus A1 is equal to 0. This is the constant equation. Okay. Okay. So what I will do, I will rewrite these equations. Okay. How I will rewrite? So M1 times A1 plus 0 times A2 plus, oh, sorry. Uh, okay. So plus 0 times A2. Again, I made the same mistake. I had to write minus here and I am writing. Okay, minus T equal to 0. And similarly, we have M0 times A1 plus M2 times A2. And then there is plus T equal to 0. And finally, we have minus A1 plus A2 plus 0 equal to 0. Here it was not 0, here it was F. Is this clear? What I have done?
Yes, sir. You have, sir, shift all the T and F
Okay,
to the left side.
okay. Yeah. I have written these equations like this. Okay. M1 A1 plus 0 times A2 minus T equal to 0. 0 times A1 plus M. So in each equation, I have treated 3 as a variable, A1, A2, and T. In first equation, we have coefficient for A1. We don't have coefficient for A2. We have coefficient for T. Similarly, in second, this, and third, this. Okay. So now I can again write these equations. This is very important. Why I am saying, because this is very simple system. And for this it is easy to get this thing, but for complex systems, you will see how powerful this method is. So this is 0 and this is M2 and this is 1 and this is -1, this is 1, again this is 0. If I make any mistake, let me know. Uh, and here I can write as A1, A2 and T, which is equal to 0, F and 0. Okay, is it all right? Everything correct?
Okay, sir.
Okay. So basically we have this matrix and you can see everything here is constant. So I will just call this matrix as A. What happened? A. This is okay. So I will call this matrix as A and I will call this matrix as Z dot. Okay, this is just a name I am writing. Why I am writing this reason, and I will call this matrix as B. So basically, and this, what is this? This is the equation of motion for our system. And we can write this as A zeta dot equal to B, where A is 3 cross 3 matrix, Z is nothing but 3 cross 1 matrix, and B is also 3 cross 1 matrix. Okay. So sometimes this is also called as mass matrix. This is also called as mass matrix. And you should see why it is called as mass matrix. Even though here it is visible that there are masses, but it is always known as mass matrix, where there are, like you will also solve some systems where there will be no mass. Okay. This is obviously variable vector here, which we are searching for. We are searching for A1, A2, and obviously tension, which is a constant force. And this is known as force vector. Huh? These are the, because here it seems that the external force are being stacked in this vector. Is this clear?
Yes, sir. It is clear. But sir,
Okay.
but
Yeah.
sir, T T is a force. Force.
F F.
T is a force. Sir, why should we not write it on the edge it left right side, sir?
Okay. So this is not the external force. What I am saying that this is the external force, isn't it? This F is the external force and T is not the. I am not saying that whatever is coming on this side, uh, everything is
Yeah,
like, yeah,
actually, sir, I'm talking about A1 and A2 and T. A1, A2
yeah,
are acceleration and T is a force. That is why
yeah.
I
So
was.
you can, okay. So you can see that even if A1 and A2 are accelerations, so you are multiplying them with the M1, okay, and T you are multiplying with some constant. So
Oh yes, yes.
treating in terms of, you should look these in terms of numbers. Don't look to these equations with dimensions, because see why I am saying that these are the equations of motion. So is my cursor visible?
Yes,
Yeah.
yes, sir. Yes.
Okay, my cursor is visible. Okay,
Like
so why I am calling this as equation of motion. Basically, we are searching for this A1, A2, and T. At every instant of time, you know this thing. There is M1, 0, M2. You know this thing. This is a constant. So every time you know this A, and you know this 0, F, and 0, which also is a constant. But every time you will not find this as a constant. There will be some variables. Okay, and here this is also a variable. Maybe F is not a constant; is a function of time. So each time this value will be different. But each time you want this vector a1, a2, and a3. So you want this z dot vector. How will you get this z dot vector? So in MATLAB, we have a command, so you can get this z dot equal to a modulo b. This is a very famous or powerful tool or powerful function in the MATLAB. And you might have seen some t-shirts on which this equation is being written. So this is a very powerful. So if you are somehow able to get this type of structure of equations, you can solve, because this is a linear, these are linear set of equations, isn't it? And you will be surprised that in most of the cases you will get the equations as linear equations in terms of acceleration. We will solve more problems and then this will become more obvious. So sometimes you might be thinking that why are we making things complicated, although there are simple models. But why I am saying that when you go to the more complex systems, this method is very beautiful and very easy to follow. Okay, you don't have to do anything. MATLAB will do everything for you, but give MATLAB the good commands, good directions, and good matrices. And MATLAB is very good at handling the matrices. So this is the reason why we are trying to write our equations in this format. Is it clear?
Okay, sir.
Okay, so this method is also known as DAE method. Why? D stands for differential, A stands for algebraic, and E stands for equation. So basically, if you see these three equations, what are these? These are A1 is nothing but x1 double dot, A2 is nothing but x2 double dot. So this is the equation. This is the equation, but these are the differential equations, and these are algebraic in nature. That is why we call this method as differential algebraic equations method, DAE method. Okay, and you have this A matrix, you have this B matrix, you can find zeta dot. And don't forget that in every simulation we try to find this zeta dot and we put this zeta dot in our my RHS file to simulate the things. Okay. Okay, let us go to now a famous example, which is a pendulum example, and try to solve this pendulum problem. And let us see how this approach, which I just mentioned, that is DAE approach, how we can solve this pendulum problem. Okay, is everything clear? Any question? Any confusion?
No, sir. Go ahead.
Okay, okay, good. So this is a pendulum problem. Okay, just one thing before we go to this, before we jump to this new problem, let me raise a question here. Uh, why I'm doing this? Okay, let me pose a question. So basically, we had this problem M1, which was connected to M2, and F of T was the external force. Okay. So, and there was a constant of length between the two. So, we saw that we do not know what is the tension in or the constant force in this massless string. We don't know. So, but is there any other way we can solve this problem? Do you think there is some other way? Because I told you that there is no such law which can tell you what is the constant force. Like we have laws for gravitational attraction or the force of attraction or repulsion between the two charges, and so on and so forth, like drag force, other forces. We don't have constitutive law for these constant force. So is there any other way to solve this problem? Okay, I will just mention there is one approach you can do while you will be simulating these things. You can try one method, that is take this M1 and connect it with spring, take M2, and the problem is same. There is no difference. So how is this problem different from this? I will call this problem as problem first, and I will call this problem as problem second. So how is problem first different from second? And I want problem first to be solved through problem second. So can you tell me how it is different?
In problem second,
Yeah,
the tension in the spring is a
the
function
tension in
of
the, yeah,
x.
is function of x. Yeah, the separation between the two masses.
Yes, sir. Yes, sir.
Okay, so that is why I am saying I am replacing the first system by second system, because in second system I know the force, I know the force using what is this known as? Yeah,
Second law of
I
motion, sir. Right?
forget. No, no, no.
Constant.
If you have if you have a spring, the force, the restoring force is directly proportional to the displacement. What is this?
Is
Yeah,
ax.
yeah. What is this law known as?
Hooke's law.
Hooke's law. Yeah, good. So I have Hooke's law and I can use it. But here, what I can do? So I am trying to solve the system first by replacing it with the second. But I can't directly replace it, because if I try to solve second is altogether different system.
Yes,
So
it is different.
how am I going to solve first using the second? Any clue
Just
or any
using,
idea?
you want to
Yeah.
solve a problem, sir, by using the second method.
Yeah. Okay. So what I will try to do. So
Sir,
if
sir,
F4, yeah, yeah.
can I say that difference between the positions of M1 and M2 is nothing but the displacement change in the length of the spring?
Yeah, obviously. So if we assume that at initial time the length of the length of the spring was normal length, so we can say that the, for example, if L is the normal length, okay, L is the normal length, and x1 is the position of this mass and x2 is the position of this mass. So x2 minus x1, this is basically the length of this spring, and L being the normal length, okay, where there is no force. If M1 and M2 are separated by L length, then there will be no force in the spring. Assuming that at any instant of time, now this M2 is at x2 and M1 is at x1. So x2 minus x1 is the instantaneous length of this spring. Okay. So this is x2 minus x1. But what was the normal length? That was L. So subtracting L. So this is the extension in the spring. And if we multiply this by K, so we will get the spring force, okay, which might
Yes, sir.
be, here I am taking it as the, uh, what, uh, that is restoring force. Okay, it can
Yes,
be like compressive as well as tensile force. but here I am assuming that it has been stretched. Okay, so this is the amount of force. So now I can write for M1, I can write that there is a spring force Fs in this direction, and there is no force in this direction. Okay, for M2, I can write that there is F in this direction and Fs in there. And I know everything. Here, nothing is unknown. In previous case, we had this tension which was acting here that was unknown. So I have solved the problem. But the thing is that I have not solved the first problem. The first problem is that the masses are separated by L length. And here you can see that when you apply the force, the length between the two masses changes. So, and what is the length between the two masses? X2 minus x. And it needs not be equal to L. Okay. But I can approximate this to this system. How? If I take the spring to be very stiff, if I take the spring to be very stiff, then I can
Yes,
approximate that if I am applying some force, there will be negligible extension in the spring, and then this will approximate this first system, and I can solve. But there is a problem. Sorry, there is a problem. What is the problem?
problem
There is a problem in doing.
doing that.
So yeah, in doing that, so we can take, so we can, so we can take this k very tending to infinity, and we can solve. So this will replicate this first system, but there is a problem, and the problem lies with the ODE you will be using. When you try to simulate this thing in MATLAB or any other software, and in order to integrate this thing, you need very stiff ODE. Why I am calling stiff ODE? Because when you are taking K K having a very high value, then this system will oscillate with large frequency. So there will be a very high frequency with which M1 and M2 will oscillate due to this high high value of K. Okay. And due to that, if you try to use OD, you have to use very small steps of time. That is why I call it as, I don't, like people call it as step OD. And there will be a huge computational power, okay, load on computation. So that is why we don't use this method. But when you are doing the simulation, you can use it and approximate. You need not take the k trending to infinity. You can take some finite value and then see how it is a good approximation to this system. Okay. And this should also give you some feeling why we are using the constant force. I am sorry. One minute. Okay, so this should give you a feeling that why we are. So in reality, this string, which I am saying, this is very. This is not something which is stretchable, but you can consider it as a very stiff string, and you can swallow it. In reality, it should be like this, but we can't swallow it, and I have already told you what is the reason. So we shift towards the constant force, and by constant force, we assume that there is some force T acting on, and then we do whatever I already, uh, whatever I showed you. Okay, so let us go to this problem, that is a pendulum problem. So here, what we have a pendulum, that is this mass hanging down on this ceiling. This is attached to this at this position, and we are attaching a frame, that is x and y axis, to this. L is the length of this massless rod, which connects this mass to this hinge point, and acceleration is acting downwards. So xy is the coordinate of this mass at any time, and er hat is the unit vector in this direction. So unit vector in this direction is er. Are you, is it clear?
Yes, sir, it is clear, but ER.
Er is a unit vector. Like we have I cap in this direction, we have y cap in this direction. I am defining er hat in this direction, and
Okay.
see that this unit vector will be in this direction when mass is here. When mass is here, it will be in this direction. When mass is here, it will be in this direction. So this is radially outward unit vector. It is not something which is constant like I and j. Okay.
Yes, sir, it is radial vector. Yes,
Yeah, yeah.
it is changing.
So yeah.
Change.
So yeah, it is not tangent, it is radial. Tangent means this.
Sir,
Okay.
I said it changes with M as M changes.
M doesn't change, the position of M changes.
M, sorry, yes, position of M changes. Yes.
Yeah. Okay, so let us draw the FBD for this mass, that is M mass. So this is M, and we cut this rope or this rod here. So there is a tension acting in this direction. And there is obviously the mg gravitational force acting downwards in minus j direction. Okay, so what is the net external force acting on this mass? Whatever it is, that is equal to mass times the acceleration of this is the linear momentum balance. Okay, f total external is mass times acceleration of this body. And what is F external total? It is nothing but the gravitational force and the string force. The string is applying the force in this direction, and the gravitational force in. These are the two external forces to this mass. See, I am taking the mass as my system, and then everything else is the external force to this mass. Okay, so it is gravitational force plus string force. And now what is this gravitational force? It is nothing but mg in negative y direction. That is why I have put minus and j. Similarly, what is F string? That is some tension uh, times ER, but it is acting in a negative direction to the ER. Okay, so I have put negative. Okay, now what is ER? So ER is basically nothing but position vector of this mass. Okay, let us go to whiteboard. Uh, okay, so we have this hinge point and we have this mass. This is X I cap, this is J cap, this is X axis and this is Y axis. And I am saying that this is nothing but the position of this mass, which has a coordinate of x comma y. And I am defining the unit vector in this direction as ER cap. So we know, so basically this ER cap is nothing a unit vector in R direction. And we know if we want to find unit vector in any direction, it is equal to the vector divided by the modulus of the vector. Okay, so that is why I have written this ER cap as R upon mod of R, where R is nothing but xi plus yj. These are the x component of position and y component of position. And then acceleration is nothing but double dot. What is this acceleration? This is the acceleration of this mass m, because R is it is position. If we double differentiate the position with respect to time, we get R double dot, and that is the acceleration, this acceleration. Okay. And that is nothing but x double dot. See, R is this, R dot will be x dot plus y dot. R double dot will be x double dot y double dot. I and j are constant. See, there will be no derivative for this I and j cap. Is it fine?
Yes, sir.
Yeah.
Clear.
So there will be no different derivative of I and j. But if you try to differentiate the
Yeah.
ER cap, so
Yes, sir.
there will be derivative, okay? But I am
Yes, sir.
not doing it here and we don't require at this time. So, but I am just informing you that there, if you try to differentiate this, don't think that when we differentiate unit vector, it is always zero. No. If a unit vector is a constant vector, then its derivative is zero. And not always the unit vectors are constant vectors. Uh, Try to swallow this thing. The unit vector is a vector whose magnitude is 1, but its direction may change. So it has a magnitude of 1, but it might have changing direction. So, and if a vector changes its direction, it means that the vector itself has changed. And if any vector has changed, it might have taken time. So when you find the derivative, you will get the derivative. Okay. This was a small point which I not try to make here. Okay. So this equation, that is f external is equal to m times a. I replace this f external total by these things. I get minus mgj minus t, c, t minus t er. Er was nothing but r upon magnitude of r, and r is nothing but xi plus yj upon mod of r is under root of x square plus y square. Okay, and that is equal to a, m times a, and this is m times a acceleration. Okay, everything what I have derived here, I substitute it in this equation 1, and I get this equation. Okay, now the constant is that under root of x square plus y square is L. That is the distance of this mass from this origin is always L. This is the constant that we are saying that uh, this string is not stretching. Okay. Squaring both sides, we can get x square plus y square equal to L. Again, see, like in previous, we had this free body diagram, but there was constant. So we took the free body diagram for mass, and then we add the constant equation. Here also we are trying to uh, put the constant equation there, but the constant here is in terms of position. We need to get it in terms of acceleration. So we differentiate this, we get d by dt of x square plus y square is equal to d by dt of L square. So differentiating this, we can get twice x dot. That is, this is the chain rule. Differentiate this, that is 2x, and then x dot. Similarly, this equal to 0. Okay, again differentiate this. So differentiation of this using UV rule, differentiation of first will give 2x dot, and x dot will be same, plus take this as u and this as v, then differentiation of x dot is x double dot. So you get twice x dot square plus twice x double dot. Similarly for this 2y dot, you will get these two terms. Okay, you cancel out the 2, you will get this equation. So x double dot plus y double dot plus x dot square plus y dot square equal to 0. So see what we are trying to do. We are trying to get the equations of motion for this mass. But the thing is that we have a constant force T and we don't know this constant force. So we have applied linear momentum balance equation. We have got this equation. So how many variables we have in this equation? Can you tell me?
Yes, sir. Wait. Sir, T and 1, 2, 3, sir.
Yeah, which one?
T
Yeah,
acceleration of
that is
in
x.
x direction and
That,
acceleration in y direction.
okay, that is x double dot and y double dot.
Yes, sir.
Okay, so these are the two unknowns. See,
Okay.
you can also argue that x, y are also unknown. But see, we are doing everything in MATLAB and we are assuming that we know the position of the mass. Okay, so at any time we know the position of the mass, but we
Yes.
don't know the acceleration.
Yes.
Okay, so acceleration is something which we don't know. So x double dot is unknown, y double dot is unknown, and this tension is unknown. So we have two unknowns here. But how
Three.
many? Yeah, sorry, three unknowns. How many equations are there?
Only one.
Only one. But let me tell you that these are not only one. This is a one vector equation, and this vector equation contains two scalar equations. You can write the equations in terms of x coordinates, and you can write it in terms of
One
j coordinates.
record.
Yeah, j coordinate. Okay, so you will get two scalar equations. So basically, we have two equations, but we have three variables. So we can't solve this for t, x double dot, and y double dot. So this is the problem. And then what comes to our rescue is the constant equation. So we have this constant equation, we differentiate it, and we got the third equation.
Sir,
Okay, so
sir,
yeah,
what you say about that? It is a vector equation, and we can resolve in two.
yeah. See, I'm doing that. So
Okay.
we have this equation.
Yes.
So expand this equation. You will get minus mgj minus txi divided by under root of x square plus y square minus tyj divided by under root of x square plus y square equal to x double dot I plus y double dot j times m. Isn't it?
Okay.
Okay, so comparing the uh, j component, okay, comparing only j and comparing x on both sides, we will get this mx double dot equal to minus t by under root of x square plus y square x. Taking on this side, we get mx double dot plus t divided by under root of x square plus y square x equal to 0. Okay, is it clear or I should
Yes, sir. Yes, sir.
explain? Huh?
Yes, sir. It is clear.
Is it
Clear.
clear? Okay, so we got this from this. Again, comparing the y component, so you will get this. So now we have this equation, these two equations, this and this. These were curved into the one, this vector equation. Okay, we got two scalar equations from them, that is this first and second. And we have this equation also there. This is the constant equation. And I have rewritten it as this. X double dot plus y double dot plus. So we have three equations, 1, 2, and 3. See the
Yes.
structure I am writing these things. This I have done deliberately. M times x dot plus x by L times t, my double dot plus y by L times t equal to minus and x double dot. Okay. So what are the unknowns? X double dot,
Y
y
double dot
double dot,
and
and
T.
t. Okay, so we write these three equations in terms of matrices.
But
How? X double dot has m as the coefficient, y double dot is not here, so it has 0, and t has x by L, so this is x by L. So m times x double dot, 0 times y double dot, x by L times t. This is the first equation equal to 0. This is this first equation. What is the second equation? My double dot plus y by L, y double dot, y by L, t. I have made a mistake here, isn't it?
Y and
So there was 0 in x. Okay, let me correct it.
the M
Okay.
replace M with zero. Yes, sir. Replace M with zero.
Yeah, so it should be 0 here, m should be here, and here it should be y by L. So I have made a mistake. Let us correct it here. Uh, okay. So what was the equation? I think I have. Oh, thank. What do I have equations here? I can write them. M2. Okay, so what were the equations? These were M
mx
x double
double dot plus
plus t by under root of x
m
square plus y square
x
x
equal to
equal
0.
to 0.
M
And then
0 dot x dot.
oh, just I will rewrite this equation. Okay.
Yes, sir.
I need to rewrite this equation. The reason is that uh, okay, I need to rewrite it. So m x double dot
Plus 0.
plus x, yeah, 0 times y double dot plus t by, sorry,
L
x by L times t equal to 0. This was the first equation. And the second equation was m y double dot
plus 0.
plus,
Plus
oh,
0 dot.
yeah. Good. Uh, okay. So the second equation was 0 times x double dot plus uh,
My double dot.
m y double dot
Plus
plus
y by L.
y by L t equal to minus mg. Okay. And the third equation, that is the constant equation, that is x double dot plus y double dot plus 0 times tension. There was no tension. Okay, so this was x dot square plus y dot square. Okay,
Okay, sir.
everything fine.
Fine.
Okay, so we can write these equations in terms of a matrices. How? M 0 x by L 0 m y by L, and this is x, this is y, this is 0, and the variables are x double dot, y double dot, and t equal to, so this is 0, this is mg minus x dot square plus y dot square. Okay, is it clear?
Yes, sir. It is okay. Okay, yes, sir. It's clear.
Okay, so this is a matrix A. See, this now this matrix is not constant. It will depend what is the position xy, and xy position continuously changes, isn't it? So this A matrix will continuously change. And
Change.
also this matrix will also continuously. That is what I was trying to make you understand in the previous section. Okay, so
Okay.
this is our z dot, and this is equal to, this is our b. So we are in search of z dot. So z dot is equal to a modulo b. So what MATLAB will do, MATLAB will calculate at each instant of time, it will calculate this matrix, that is A matrix. At each instant of time, it will calculate this matrix, that is B matrix. And then it will do A modulo B, and it will return you this Z vector. So what Z vector is actually, it is X double dot, it is Y double dot, and it is T. So at each instant of time, you will be getting the values of your Z dot. And when you are getting your Z dot, you will give this Z dot to ODE, and rest of the thing will be done by ODE. That is, that will integrate these equations to get the new values for x, y. Okay, and for x dot, y dot. Is it clear?
Clear. Clear. Sir, why it is a z dot? Why, according to my thinking, it should be z double dot, isn't it,
Yeah,
sir?
it is Z. Yeah, it is Z double dot. But if you look to my code, when I write the code, I write there z dot. Is it? That is why. Yeah, yeah. If it makes you confusing, you can also think it as z double dot.
Because when
It
we
is.
integrate it one time, it will be z dot, then it will be z.
Yeah, yeah, you are absolutely right. This is just maybe in coding I have written it as z. Okay, let us change it. It is not a big deal, so we can change it. Let us change it here. We call it as z double dot. Okay.
Yes, sir. Yes.
Okay. Yeah, maybe it might create some confusion in you. So I call this as z double dot. Okay. So now this equation will return as z double dot, and that is equal to a modulo b. Okay, so that is fine. So you have your z as xy, vx, vy, and you have this z double dot here, isn't it? So you give this to MATLAB will solve it, and that will return you the z vector. Okay, I think we are running out of time. So we will meet in next
1:15.
class, and we, yeah.
Yeah, sir, it is 1 hour and 15 minutes.
Okay, no, I think it should be 1 hour only because we started 10 minutes late. Okay, but any question?
Mm, not till, but sir, I get a new feeling of the.
Yeah,
Uh,
so in structure you will be seeing these equations most of the time. So you will be seeing here what is known as stiffness matrix. So you will get lot of equations like this when you are doing the structure.
yes, sir. That
When you take the structures.
so 2xy sigma xy 2xyy 2z. Yes, sir. Yes, sir. I got it.
Yeah, yeah. So you will get this matrix. So if
Yes.
you are, and
Then
not only there, when you will be dealing with any dynamical system, you will see this structure there. Okay. So if you are good, if you have a good intuition towards these structures, the way we are writing these dynamical equations, so you can have a better understanding of the system. So in next class, what we will be doing, we will try to simulate this pendulum using these equations, or maybe also that two body that m1 and m2. But you can also try these, because this is nothing but a z dot vector, z double dot vector, which we were. You have to just write this code x y x dot y dot in your that function my RHS, and everything will be okay. You try it, but we will come again in next class and we will try to do it in the next class. Okay. Okay, then I think we will stop here and let's meet in next class. I will stop recording. uh,
sir,